Hi, welcome to part 5 of the video series Deriving R-squared. Today we are going to try and find the slope and the constant for the best possible line that can represent different data points in a data set. I would highly recommend watching the previous video so that this video makes more sense to you. Okay, so let's start off. We are first going to discuss a few things that will help us out in the main derivation of finding the best slope and the best constant. So let's have a look at that. Let me just change the color. Okay. So last time we left off at this point, we said that the sum of squared errors is equal to the sum I is equal to 1 to n. N is the number of data points. Y, which is the actual y value, minus y cap. Y cap is the predicted y value, the whole squared. Okay, and y cap is equal to mx I. So y cap I. Let me just add the I everywhere to indicate which data point we're talking about. mxi plus c. Okay. Now, if you think of our earlier examples from previous videos, we mainly said that if y represented the cost of a house, the cost is dependent in some way on the square foot area of the house. Okay, I'm just going to write it as square foot. Okay, so somehow dependent on the square foot area. That is why we said that the square foot area, or in this case x, was a variable that y was dependent on in some sort of way. But now let's think of our current situation. Currently, our aim is to find the best line that can represent a set of data points. All these data points are represented with all the values of x, all the xi's, right? So now think of this. Is xi still our variable? Not really. Now all the data points together are a constant because each line is being checked on the same set of data points. Okay. So then what is the variable, or what are the variables? Take a pause, think about it. Let me give you the answer. The variables now are m and c. Why? Because they are the variables that are going to decide what kind of line we are drawing. So the SSE is actually, if you think of it, a function of m and c. Because based on the value of m and c, you get a good line, and based on that, the error keeps changing. The sum of errors keeps changing. Once again, this should be E. Okay. Now we have another question over here. In previous videos, we have talked about differentiating with respect to one variable. So if y is dependent on x, you do dy by dx, you find the derivative with respect to x. But what do you do if you have more than one variable, right? So this is where the term partial differentiation comes into play. Let's think about this now. Okay, let me give you another example. This is an example I have kind of used in my previous video series, which is that the height of a tree is a function of its age. Okay, but this time we're going to say that it's a function of the age as well as a function of the kind of soil, or the nutrient, the nitrogen density of the soil. Okay, let's call it soil. Now think of this. Age is dependent on age. The height is also dependent on soil. H is for height. But is the age dependent on soil? And is the soil dependent on age? Not really. We're going to assume that these two variables are independent of each other. The nitrogen density in the soil is not dependent on the age of the tree, and the age of the tree is not dependent on the soil. Okay. Therefore, we could say that these two variables are independent variables. Okay. Now think of this. Let's say we are trying to find the change in the height with respect to the change in the age. Okay, we know that height is dependent on age, right? So any term with age in it you'll be able to derive it, you'll be able to differentiate it. Okay, but we just discussed how soil is not at all dependent on age. So is there any change in soil with respect to change in age? No, no change in soil. Therefore, the term for soil would be looked at as a constant. Okay. For example, let's take a basic function. Let's say, let's not use y over here. Let's say f is equal to x square plus y square. Okay. In this sort of a case, let me just change the color for the next part. Okay. In this sort of a case, now I'll show you the representation of partial differentiation. So del f, so change in f with respect to the change in just x. So you derive x, you find the derivative of x, sorry, you call it 2x, right? But y square is a constant because we are assuming that x and y are independent of each other and y does not change with respect to x. Therefore, you could say that y being a constant when differentiated with respect to x will be equal to 0. Like if you had found the derivative of mxi plus c with respect to xi, with respect to x, c would have become 0. So y square plays the same role over here. Similarly, the partial differentiation with respect to y, any guesses? You can try and pause the video and think of it. It would be 0 plus 2y. Okay, this is just a brief understanding of what partial differentiation is. If you'd like to study it in more detail, I will put a link to the Khan Academy videos on partial differentiation. But this is how much you need to know to be able to understand the next part of the video. Okay, so let's go to the next part. So now that we know that m and c are variables, we need to differentiate the sum of squared errors with respect to m and with respect to c to be able to find the values of m and c. Okay, so first our aim is going to be to find the value of c or the constant. So what we are going to do is, first let me just write down, once again let me change the color. Okay, first what I'm going to do is I'm just going to write down the formula of SSE. This time I'm going to substitute y cap with mx plus c. Okay, and I'm going to write sum in this way. It's an easier way of writing it. It talks about I going from 1 to n. Okay, so this is equal to y minus mx, because y cap is equal to mx plus c, so minus y cap is minus mx minus c. Let me add the i's so that we know we're talking about a specific data point. Okay, and we square the entire thing. Now if we want to find the value of c, we are going to partially differentiate SSE with respect to c. Reason? If you find the change with respect to m, c will not be used at all. Okay, we are trying to find the change in SSE with respect to c to be able to find the constant, to understand how should the constant's value be such that the best line is found. Okay, that is why we're going to differentiate it with respect to c. So del of SSC by del of c is equal to, now what's going to happen is you're going to mainly differentiate this term and just sum up those differentiated terms. Okay, because each term in the sum is going to be differentiated in the same way, and we had seen that the sum of many terms can separately be differentiated. Okay, now in this term you'll have to use the chain rule. Once again, let me write this part first. So that makes it 2 times yi minus mxi minus c, and then we multiply the differentiation of the actual term, the base, which is, now yi is always going to be a specific value, means it's a constant. So when derivative with respect to c, you'll get a 0. M and xi are again constants. M is a constant because here you're finding the derivative with respect to c, and xi is again another value like yi. So this is also 0, and minus c can you can find the derivative of minus c, which is equal to minus 1. Okay, so this is equal to minus 2. I'm bringing out the constants. Summation of yi minus mxi minus c. Now what do we do? To be able to find the best value of c, think of it. If you've watched the first video, you'll kind of have an idea of what you can do over here. You can equate it with 0 to find the minima, right? Okay, now another question may come into your head. How do we know if this equating with 0 is going to give us the maxima or minima? Now think of it logically. Okay, you found a line. You keep increasing the distance of the line from each of these data points. Till where can you keep taking the line? It can go so far away. You can keep increasing the distance. You'll never find a maximum distance at which the line can be kept. It can go till infinity. This means that there isn't actually a maxima available when taking the sum of squared errors. Therefore, when equating to 0, you can only find a minimum value. Okay? So now, let's try and equate these two. So, what we're going to do is we're going to again separate these three terms and sum them up separately. So, what we'll say is that minus 2 times summation of yi minus m summation of xi, I'm taking out the constants, okay, minus summation of c, okay, or you could write c summation of 1 because it's c times 1, okay. Now this is all equal to 0. Now the minus 2 can be you can divide both sides by minus 2 and you'll get 0 on the right hand side, and minus 2 will go from the left hand side. So this will be equal to summation of yi minus m summation of xi is minus c with the summation of 1. 1 being added to itself n times is equal to n, right? So it would be n times c, which is equal to 0. Okay. Now let's get c on one side so that we know whatever c is equal to. This is equal to summation of yi minus m summation of xi. Now let's divide n on both sides. You'll get this summation yi by n. I'm just separating the terms here, okay, for ease of understanding. Xi by n. Now this summation of certain values divided by n is going to remind you of something from our second video. It is the sample mean. I've put in the formula again over here at the top. Okay, so it basically says you can add up all the values of x and divide it by the number of values you've added, and that will give you the average or the mean. So you could write it in this way, that this is equal to y bar, c is equal to y bar minus mx bar. So over here you'll notice that the constant value is dependent on m also. So once we find the value of m, we'll be able to substitute it over here and even find the value of c. So let's go to the next part and try and find the value of m. Okay, so we start off in the same way. What we are going to do is, we are this time, let me first change my pen color. We are going to find the derivative of SSE with respect to m, right? Okay, so first let me actually first write down what SSE is equal to so that it's easier for us to find the derivative. Okay, So SSE is equal to summation I yi minus mxi minus c the whole square. Okay, now let's find del SSE, del m. This is equal to summation I. We again use the chain rule, right? The first part is going to be exactly the same. It's the next term that's going to be different because we are derivating with respect to m this time. So yi is again going to be 0 because it's a constant. Now the next term, you have xi, which is a constant, and m can be the derivative of m can be found with respect to m, which gives you a 1. So you just have xi over here, and c is a constant, so 0. Okay, so this is equal to 2 times summation I, and I'm going to multiply each term. I'm going to add this minus over here, okay, and I'm going to add each term over here. So this is xi yi minus mxi squared minus cxi. Okay, now the same thing, it has to be done. You have to equate it with 0 to find the best m such that you get the best line which has the minimum sum of squared errors. Okay, minimum value of the sum of squared errors. Okay, so we're here. Now let's separate all the terms. Again, the minus 2 will go away. So let's see. So summation I xi yi minus summation I mxi squared minus cxi is equal to 0. Now let's add these second two terms on both sides such that you get only positive terms on both sides. Okay, so summation I, that's an I, okay, xi yi is equal to summation of mxi squared plus summation of cxi. Okay, now once again I forgot to add the summation sign in the previous line. There should be a summation over here. Okay, now what we're going to do is we're going to add the actual value of c and expand the second term. Okay, let me add it in green color. That will make it more legible. Okay, so this is summation of mxi squared plus, now c is equal to y bar minus mx bar. So we first say y bar times xi, okay, and then we have minus m x bar summation xi. Okay, now let's get the m terms together. So over here you have m times summation of xi square minus x bar summation xi. Okay, and we add the other term also, summation, sorry, plus y bar summation xi. Okay, now what we're going to do is we're going to bring the non-m term to the other side. Okay, so we'll just swap the sides. So we're going to say m times summation of xi squared minus x bar summation of xi is equal to summation of xi yi minus y bar summation of xi. Okay, this means that if we divide both sides by this term over here, we could say that m is equal to summation of xi yi minus y bar summation of xi divided by summation of xi squared minus x bar summation of xi. Now, if you have a look at this over here, because you're only using the data points that you have, the y values and the x values of each data point, you will be able to find the value of m. Once you find the value of m, it's easy to substitute that number in y bar minus mx bar, and you'll even find the value of c. So there it is. That's how you find both m and c. Okay, I'm going to highlight this value of m so that it's more legible. Just give me a second. Okay, let's take a nice bright color. We've already used red, but I think red is kind of the brightest. Okay, let me try and... Okay, it's cutting it off a little bit. Here. There. And that is the value of m. Okay. Okay, then that's it. Just one small thing over here. You may see, once again, let me just... You may see this minus sign over here. It's not a part of it. Okay, it's just that much. Okay, then that's it for today. Next time we'll understand a little more about how we're going to go about the R-squared part of the derivation, understand how to use these things with respect to R-squared. So have a great week and I'll see you in the next video. Thank you.